I can do a little bit better than that too. So I've confined the places where the derivative must be 0, because those are the places where the tangent line is horizontal or has 0 slope. But over here at point P, it looks like x coordinate 5, maybe y coordinate 1. We've estimated the slope of this tangent line just by drawing in a triangle. So we've got the tangent line here. It looks to have a base of about 2 units wide and a third leg of 3 units tall. So that slope should be about 1.5. That tells me when x equals 5, f prime of x should be about 1.5. So steeper slopes like this, well, first of all, they better give me non-zero values. And I can estimate that just with the geometry of the picture. So this allows me to think about derivatives even in cases where I don't have a formula for the function. Now, when I look at this graph, I see that there's places where there are horizontal tangent lines. Those are all places where the function is neither decreasing nor increasing. The places where the function is increasing are going to have positive slopes, right? Because if my function is increasing, my tangent line had better be reflecting that the function is increasing, and increasing slopes means positive slopes. For the very same reason, decreasing functions should have a decreasing tangent line, and a decreasing tangent line has a negative slope. I can get rid of the word tangent there. I can just say a decreasing line has a negative slope. And now I'm tying that into my new idea of slopes of tangent lines. So everywhere I see the function is decreasing, I'm expecting the derivative of the function to be negative. I'm expecting the graph of the derivative to be below the x-axis. Everywhere my blue function is increasing, whether it's starting below the x-axis or above it, doesn't actually matter. I just want to know, is the function increasing? And as long as that's true, then the derivative should be positive. So one of the ways that I know that this pink line is the derivative of the blue function, the blue curve, is that the pink curve is always negative when the blue curve is decreasing. The pink curve is always 0 when the blue function sort of flattens out in these 3 points. And the pink function is always positive when the blue function is increasing. So again, I haven't actually done any algebra here. I don't have formulas for these functions, but I can identify this relationship just going off of the picture. Now let's take a look at a function where I do have a formula. Here we've taken f of x equals the square root of x. And I haven't proven this yet, but the derivative of this function is going to be another function whose formula is 1 divided by quantity 2 square root of x. We'll do this maybe in my next video here. Now, how do I know that this blue curve has this pink curve as its derivative? Well, I see that the blue curve is always increasing everywhere I go. So my pink curve is always positive. It's always above the x-axis everywhere I look. I have a much steeper slope closer to the origin, and I see that my steeper slope has a much larger magnitude of the derivative, right? So these are all positive numbers. They're all getting larger as my x goes to 0. That should make sense from the formula because my denominator is going to 0. But geometrically, that's telling me that tangent lines drawn close to 0 will have very large, very positive slopes. The farther I go out, the blue curve is flattening. It's still positive, but the slope is getting shallower. So I see that in the picture, that the derivative of this function is getting smaller. It's tending to 0 as x grows.